Alright, welcome back to our slides on sets. We're going to finish them up and then get to a new set of slides today. So, we talked about strings last time. That's where we ended up. So we were like making pairs and then triples and quadruples and then n tuples. And if we include characters, now suddenly we have strings. It was wonderful. And now it's time to talk about just sets in general again, talking about partitions of them. So this is a very in English, a very simple concept to explain, but as math goes, it gets a bit fancy in the definition of things, but that's okay. We're going to get through it together. So let's start with two sets. We say that A and B, they're disjoint if they don't share any elements. So for example, if I had my A, if I could draw, if I had my set A as like 1, 2, 3, and then my set B was like 4, 5, 6, those are disjoint because they don't share any elements, okay? They don't share any elements, which means if I intersected them, I get back the empty set because there's nothing in common. Yeah? So that's what it means to be disjoint, and maybe you have more than two sets, like you have A, B, C all the way to Z, for example, and maybe A1 to A55, things like that. So if you have a sequence of sets like this, we say that those are pairwise disjoint if every pair, like you can take two of each of these, and that pair itself is disjoint. So any possible pair of that sequence of sets is disjoint. That's what it means to be pairwise disjoint. So that's saying, okay, pick I and J, some indices, like, I don't know, A34 and A57, make sure that that itself is disjoint, and do that for every possible pair I and J where I is not J, because obviously, like, A34 is equal to A34. Those are not disjoint, but any other set should be disjoint. Okay, so that's what it means to be disjoint. And now if we kind of use that with an extra side condition, we can what's called partition a set. Okay, so if we have one set, call it S, we can partition it into a bunch of non-empty subsets. So we can make another sequence of sets, and each element of S, we say, is in exactly one of those subsets. So I'm going to show you an example in a second, don't worry. So again, you make a sequence of subsets, and we say that that sequence is a partition if they're all subsets of S, so they're all contained inside of S. S contains them, that is. And then they're all non-empty, because it wouldn't make sense, because we're trying to partition the set. We could just get rid of the empty one, so we don't include any empty ones. And then all of them, every set in that sequence is pairwise disjoint. That's the third condition. And the final one is, okay, it partitions S because if you union them all together, they become S itself. So you do this union on each possible one, this entire sequence at once, you get S back. Okay? So this is a lot to take in as a definition of something, but it's very, very simple to explain in a picture, I promise. So let us come up with a three-set partition of the following set. We got raccoon, koala, squirrel, cat, and dog. Yeah? Here is it, made lifelike. So all we have to do is make three sets that partition this set, and this is how you draw it. Okay, maybe, I don't know, squirrels and dogs can go together, because dogs like chase squirrels, yeah? And maybe cats and raccoons go together because, I don't know, they're both angry. Things like that. And so we have koala sitting by himself, but we now have made three subsets. That's the idea. So we got this one of just squirrel and dog. Then we have cat and raccoon, and then koala by himself. Okay? So those are our three subsets of C, and watch, we got like C1 equals, I don't know, koala, C2 equals squirrel dog, and then C3 is the last one. C3 equals raccoon, cat. Okay, so let's check that this is a proper partition. It's very easy to do. Are each of these subsets of the entire set itself C? Yes. That's just the way we did it. They have to be. Like, I'm only taking stuff from C to make my subsets. Okay? And then, okay, are they all non-empty? Yeah, They all at least have one element in them. That makes sense. Are they all pairwise disjoint? We can try this. Try every possible pair of things, make sure that they're not in this, they're all disjoint. But it's easier to see that, okay, yes, we only use one of those elements in one of the sets. Like koalas nowhere else. Squirrels nowhere else. Pairwise disjoint automatically. Okay, and then finally, do they union together to be the whole thing? Well, yes, that's the way that we did it. We can just union together this, this, and this, and suddenly we have C back. Okay, so that's what it means to be a partition. You're just splitting it up, that's all, into non-empty subsets. And if you think about it this way, it's quite easy to always make sure that they're pairwise disjoint. Okay, so that is a partition. Not too bad, I hope. Okay, the math is weird to define it, but it should make a lot of sense. It makes sense to want to do that as well because, like, we want to put similar things together sometimes, and we'll get into that later in this class. Okay, so let's give you an example now to try yourself. So go ahead and see if these two things hold. So do A, B, and C, defined up here, A, B, C, and D. Do A, B, and C form a partition of R, which is the real numbers, remember? And then do A, B, and D form a partition of R? So think about that, and then we'll come back and do it together. Okay, so assuming you have tried your hardest, let's try A, B, and C. So let's check all our conditions. Dun, dun, dun. Well, the first thing, probably the most important thing, is do they union together to be all of R? So this would be everything less than -2. Okay, so that's everything on this side of the number line. So here's -2. It's like not including it, but that way. So that's A. And then B is kind of the same thing with, there's 0, there's 2, not including, but B's all this stuff over here. Cool. So we better include this right here with C if we want it to be a partition, right? So let's see. So it's everything less than 2, whose absolute value is less than 2, so every x. And oh man, that's all this. Yes, that's all this right here. That's C, but it doesn't include -2 and 2. You see that? If you union them all together, it's not the whole thing because we're missing -2 and 2. We're not including any of those. Do you see that? So they cannot be a partition, A, B, and C. So the answer is no, because A union B union C misses, if only I can draw a brace properly, misses -2 and 2. Okay, they have to union together to be all of R. Okay, we say it's like not R. It misses those two elements. All right, now let's try A, B, and D. And what is D but the proper thing that includes, bam, -2 and 2. That's D right there. You see that? And so A, B, and D, yes, they union together to be all of R. That's good. That's quite nice. So let's check all our things. They do union together to be R. Okay, what else? They're all subsets of R, yes. There's not any extra stuff. They're not like including a pair of things or something like that. That's fine. They're all pairwise disjoint. Do they not share any elements? Let's see. It doesn't look like it. A, D, and B, they're all, and A and B miss 2 and -2. So it looks like they don't miss anything, or they don't share anything. So they're pairwise disjoint, and are they non-empty, all of them? I think so, because D has some elements in it, A has some elements in it, and B has some elements in it. Cool. All non-empty. So that's our 4 conditions. So yes, the answer is yes. They form a partition of R. And this one was new. So hopefully that's making more sense now, and you can see how it might be useful. Like, okay, I want to make sure that my program only ever considers A, D, or B, and I don't want to like overlap anything because I want to do different things in each case. Yeah? So that is partitions in a nutshell. You're now professionals. So now let's talk about sets in programming, because you should have seen by now at least the set type, right? That is in C++, you can include set, right? And set of any type T is just a balanced binary search tree. Okay? So we are pulling the mask off of the representation of these things. So set of T is just a balanced binary search tree. It's very fast. It's got log of n lookup because it's balanced. It's guaranteed. And we use that. We use that a lot, and it doesn't have duplicates, remember. Set cannot have duplicates because it's modeling a real set. Yeah? That's the point. It's beautiful. It's all coming together. And then unordered set is a newer thing that came in C++ 11 and later, and that's just a hash table, and that has constant lookup on average. Okay, so that's quite nice. You know about sets. You've been using them, potentially. All right. So those are the nice fast ways of doing sets, and I would like to now formalize sets in Racket. That's a common thing to want to do as a logician or like a pure math programmer kind of thing. We would like to formalize things to make sure that we have some nice, easy to understand idea of what's going on. We're going to make a reference implementation, so we don't care about speed. It doesn't have to be fast. And let's just model sets, unions, and intersections, because why not? Okay, so we're going to have a few helper functions needed, and that's going to be that. We are going to formalize sets in Racket. So let's get started. All right, so I made a folder for today. Let's just make one file called, I don't know, sets.racket. And the idea is, did I already make this large? Yes. And the idea is, let's model sets as just lists. Because Racket is all about lists. It's a Lisp language. Okay? So let's model sets as lists. And if we do that, it's quite easy to make them. Okay? So we can say like define make set, and then we give like some list L. List, let's call it. Or maybe we'll just call it L. And all we have to do is give back L itself. That's the answer, right? But the one thing that is different about a set is we need to remember to remove any duplicates. So let's remember to do that from that list. Remove dupes for remove duplicates. Okay, we'll make that function soon. So yeah, that is all we have to do to make a set. So let's figure out how to remove duplicates now. So define remove dupes L. What in the world are we going to put here? So removes the duplicates from a list L because sets don't have duplicates. Okay, so for example, remove dupes of, I don't know, the list 1, 2, 2, 3, 3 should give back the list 1, 2, 3. Yeah, something like that. And so let's figure this out. It's going to have to be a recursive solution because Racket is all about recursion. So I think the idea is, usually with recursion on lists, you'll break it down to, hey, is my list currently empty or is it not empty? So cond, we will say, is the list currently empty? Is L currently empty is the question. And if it is, well, we should just give back L itself, because empty lists, that's not too hard, right? Empty lists already have all their duplicates removed. So if the list is empty, give back the same list. Give back that empty list again. Okay, otherwise we're in this case and we have some more work to do. So let's work on this. So let's figure this out now. Otherwise, list is not empty. Dun dun dun. So we're gonna need to like unpack it. So let's get the first element and the rest of the list, because that's how we unpack lists. So for example, if we were given this list right here, we would get the first element as 1 and then the rest of the list as 2, 2, 3, 3. Okay, so let's get that. So define f or FST or something to be the first thing. And then we'll get the rest in a similar way, like RST, rest-L. Okay, so now first is holding the 1, for example, and rest is holding the 2, 2, 3, 3. And the idea is we want to make sure that we get rid of any occurrences of this first element in rest because it's already there. We don't want to have it anymore. So get first, or remove all extra occurrences of, I think there's 2 R's in that, of first in rest. Okay, so let's make maybe a filtered rest. Oops. So all we have to do is take rest and filter out all the things that are not first. Okay, or filter out all the things that are first, my bad. So we're going to take this, take rest, and filter it with a function that gets rid of all of the things that are first. Okay, so we'll filter rest to remove all firsts, if that makes sense. And I'll show you an example of this on the REPL in a second. So it should look something like this. We want to make sure, we want to keep the things. It needs to return true for all the things we want to keep. So make sure that it's not equal x to first. I think that should do it. So that is the idea. So let me show you this in action. Let's pretend that we had a list, I don't know, 1, 2, 2, 3, 3 again, and oops, sorry, first of L. So the first is the 1, and the rest is the 2, 2, 3, 3. Yeah? And now the idea is we want to filter everything that is not equal to first in rest. Okay, so what is that going to give back? Maybe you should take a second to think about what it might give back. And let me show you. It is 2, 2, 3, 3 because 1 does not appear. Okay, so it took all the things that were not equal to first. Now let's redefine rest. Let's pretend that rest was, I don't know, 2, 1, 2, 1, 3, 3. Yes? So now if we filter it, we still get back 2, 2, 3, 3 because it got rid of everything that was equal to first. It kept all the stuff that was not equal to first. You see that? That's quite nice. So it's going to make sure that everything is beautiful for the rest of the list. Okay, so now let's remove the duplicates from the rest of the list for every other element. That's the next step. So new rest is, well, remove the duplicates for all the 2s and 3s, for example, in the filtered rest. You see that? That's all you have to do. Just recursively remove the rest of the duplicates, and then the final answer is first cons together with new rest. Yeah? So we'll bring them together with the cons, and that's our final answer. So that should remove all the duplicates, in theory. And let's try it. Sets.racket. Oops, I forgot that. Try it again. Okay, so let's remove all the duplicates in, are you ready? In 1, 2, 2, 3, 3. Go. Yeah, isn't that beautiful? And they don't have to be in order, like this could be 2, 1, -1. It's just going to work, okay, because of the way we did it. So please study this. Hopefully it makes sense to you. It's just recursion on lists. Okay, so that is removing duplicates, and now we can make a set. We can be like, okay, set of that whole thing now, of our L. And now we get, oh, sorry, I didn't define L in this case. 1, 2, 2, 3, 3. And now we have our set represented as a list. Okay, so that's representation. And now let's just figure out the next step. So we're going to need to figure out if an element is in a set so that we can model unions and intersections. So let's make our is this thing in function. And we can actually use this character in Racket, which is wonderful. So define in a set S. Is an element X in a set S? That's the idea. Okay? Returns true if X is in the set S. Isn't that fun? So, or maybe we should make it capitals because that's how we do stuff in Racket or in set theory. So now we just need to return true if X is in our set S. And there's actually already a Racket function that that defines this. Okay? And that function is called member. So we can just say, hey, is X a member of S? And that will almost do the right thing. It doesn't return true or false, which is why I had to edit this video. Unfortunately, it returns like the list itself where it occurs, but we can just use an if statement to get rid of that. If member XS, then true, else false. Yeah, that should work. So now, if I define like my L, it'll be easier if I just get it here. If I define L to be that list, and now we can do everything. I can say enter, enter sets. What we can do now is say define S as make set of L. And so now S is 1, 2, 3. And now we can check, hey, is like 2 in S. Something like that. There is a space there, it's just a weird character. True. Is 3 in S. True. Is 5 in S. False. Cool, huh? So that is checking for an element of. That's not bad, because we can just reuse a lot of stuff. Okay, so now we've modeled sets. We're good at that. We've got in. We've removed all our duplicates. I guess I've called it this. Now let's just model unions and intersections, and we are golden. So what is a union? So a union is very similar to appending two lists. Because remember, let's see, do we have just append? If I append 1, 2, 3 and 4, 5, 6, it just puts those lists together. Ooh-hoo-hoo. So that is how we can combine two lists to keep everything that was there. And that's essentially unioning. So define union to be like S1 and S2. Well, let's define that to be, I gotta put these parentheses around it. Let's define it to be just append S1 and S2, and then there might be duplicates, so just remove them. Yeah? Not bad. And that is union. Immediately we have union now. Isn't that fun? So let's make, like, I don't know, L and L2. This can be 2, 2, 3, 3, 4, 4. So now we can say, I don't know, define S1 as make set L, and L2 can be S2. So now I have S1 and S2. Let us union them. I need to copy the special character from here. It's hard to make that character on the terminal. Let's union S1 and S2. And so it'll just append the lists and remove the duplicates. Isn't that fun? It's perfect. That is all you have to do for unions. And then intersection is going to be slightly more complicated. Okay, so define intersection of S1 and S2. Well, now we're going to have to make sure that it's there in both. Okay, so we're going to have to go through every element and make sure it's there in both. So I don't know. Let's get every element, and let's oops. And it looks like my computer just froze, so hopefully you're still there. I'm going to I was saying that I'm going to define this every element, get every element of this set by using union that we already made. Union of S1 and S2. And then we're just going to go through every element and make sure that they're there in both. Okay, so now and check if it exists, if it's in both S1 and S2. If it is, add it to the final output set. Okay, so now that's all we have to do. Okay, so the result, well, let's call it in both, that's going to be, well, take every element and only keep the ones that are in both S1 and S2. Okay? Only keep means filter. So take every element and filter it based on whether or not it's in both S1 and S2. So are you ready? So and, well, we need a lambda. Lambda x. Is it true that x is in S1 and it's in S2? If so, keep it. And that is our in both list. And that might also have duplicates, so we just need to remove those. And then we are good to go. So I'm filtering all the stuff that is not in both. Okay, I'm making sure, only keeping the things that is in both S1 and S2. See that? Isn't that fun? And then finally it might have duplicates, so we're going to remove any duplicates. And that is intersection. We did it. So let's intersect now L1 and L2, or S1 and S2. Whee. So if I reload this, do I still get S1? I do, cool. So let's say intersect S1, S2, and S2 was 2, 3, 4, S1 was 1, 2, 3. The intersection was 2, 3. Isn't that cool? So we have modeled sets now. This is not at all efficient, but hopefully it's easy to read. It's easier to understand. So it was very clear what we were doing at each step. So that is how you model something, how you formalize something. And that brings us to the end of this set of slides. So we are done now with sets. We'll be using them for the rest of the class, of course, but I'm going to pull up the next set of slides and I'll come back there. So I'll see you in just a second. All right, welcome to the next set of slides. These are about number theory and encryption, which are two of the coolest topics that we're going to talk about in this class, so these are exciting. There's a ton that I am required to teach you about this stuff, but they all go together very well, so it's not going to be like the world's longest set of slides. And feel free to pause and admire this wonderful XKCD comic that is relevant. Okay, so the first thing that I want to talk about is division. So we have talked about this already, but let's go even further, okay? So we say that x divides y, written like this, if and only if x is not equal to 0 and there is an integer k such that y equals kx, okay? Remember that? So that's all well and good. We have more ways to say that, though. If x divides y, then y is said to be a multiple of x, and x is a factor or divisor of y. So these are all words that you have maybe heard once upon a time, and that's all not too bad, I hope. Then, something that you may have not heard before, unless you took maybe like a linear algebra class, is this concept of a linear combination of things, which is going to come in a lot of use for us this semester, especially in this set of slides. So a linear combination of two numbers is just a sum of multiples of those numbers. So it's not too bad. So if you have x and y as variables, they could be anything. A linear combination of x and y is, okay, take some multiple of x, take some multiple of y, and either add them together, because technically this could just be plus negative 42y, yeah? So yeah, that's linear combinations, and here is a funny tweet that I saw. So let us use those to do fun stuff. So let us make a proof based on those definitions. Okay, so let's say x, y, and z are integers. And let's assume that x divides y and x divides z. So let's prove then that x divides sy plus tz for any integers s and t. So that is x divides any linear combination, yeah? So I should point that out. That is a linear combo of y and z. That's important. So let's just use the definition. So we know, we get to assume it's that, assume that and that, prove that, right? That's a direct proof. So if x divides y, that means we get for free, okay, y equals kx for some integer k that's non-zero. You see that? Oh, sorry, then an x is not 0. So y equals kx for some integer k. Then we have also x divides z, so z equals, I don't know, mx for some other integer m. Could potentially be the same for ints k and m, and x is not 0. So we have this, we know this, and now we have to go and prove this. Excuse me. Which is just saying we need to show that sy plus tz equals some, I don't know, some r times x, yeah? So it's divided by x, yes? That is the idea. So we need to show something like this. So let's see if we can by plugging in our definitions. So we have x in both of these equations, so let's use that. Put that in a box, maybe. And we do need to show this for any s and t. So we're just going to keep those arbitrary. Okay, so that's what we need to show. And all right, let's just start with this side and see if we can make it look like that side. Something times x. So, okay, assume that we have some y and z. Let s and t be arbitrary ints. Okay, so sy plus tz, well, following our definitions, we have these for y and z, yeah? Plug them in. That equals s times kx plus t times mx. Ooh, this is nice, this is nice. And we can actually take an x out of that, can't we? So that is, because it's just skx plus tmx, that equals x times, let's see here, sk plus tm. And of course, we can put that on the other side if we really wanted to, sk plus tm times x. And so bam, just let r be that. It is a integer times an integer is another integer, and if you add that with another integer, it's still an integer. So this is like a nice value of r. Just pick that one, and suddenly we have this for every s and t. It's always the case that x divides sy plus tz, so therefore x divides sy plus tz. Yeah, QED. Beautiful. So that's the proof. Not too bad, just follow the definitions, unravel them. Okay, so now try this one yourself. Is it true that 7 divides 21? Explain your answer using the definition of divides. Well, I think you know that it's true, but you need to show me why using this definition, because that's how we're going to define for math, for all of mathematics to see this is exactly why this is the case. This is why it makes sense. Okay, so the answer is yes, and the reason is 21 equals 3 times 7, and 3 is an integer. Okay? Okay, QED. That's all we needed. It's y equals kx. That x was not 0, it was 3. And so, or sorry, it was 7. And we found our k being 3. Yeah, so the answer is yes. Maybe with an exclamation point. Okay, so that is hopefully not too bad. Just unfold the definitions. Always remember those definitions. It's going to be very important. Okay, so now try something a bit harder. So it's more similar to this proof. Try it yourself. For any integers a, b, and c, if you know that a divides b and a divides c, then can you always prove that a squared divides bc? See if you can prove that. And then we'll come and do it together. Let's make sure I'm recording, I think. Okay. So again, we let those be arbitrary, we assume this and this, and we prove that. Yeah? So let's just assume a, b, and c are integers. We can write proof if we'd like. Let a, b, and c be ints. We're going to show this assuming these two things. And assume a divides b and a divides c. Okay, so we need to show this, and we can get there, most likely, from unraveling these definitions as usual. So, unraveling the definitions, of course, we say that b equals ka and c equals some other thing called times a. C equals, I don't know, j a. Yeah? Yeah. For some integers, k and j. For some ints, k and j. All right. So now we need to show that bc equals some other integer like r times a squared. Yes, that's what we want to show, because that will prove that a squared divides bc. Okay, so let's figure this out. Well, is there one way to get bc using these equations? And the answer is yes. We can just multiply them by each other. Like, we can multiply the left side by itself and the right side by itself because they're equal, right? So multiply those two equations together to get bc equals these two things multiplied together, because they're equal, ka times ja. Okay, did you get that? And now, suddenly, the beautiful thing happens, kj, a squared. And oh man, multiply two integers together, you get an integer back. There is your r. And so suddenly, it all works out. So therefore, a squared divides bc. Okay? Because bc equals some integer times a squared. Whee! QED. Did you get that? This is a very good example. I hope that you did. Please yell at me if it's not making sense. Okay, so that is, yeah, not too bad, I hope. Division and things. There is a thing called the division algorithm, which is weird to think about, but it does a very, very obvious thing that you know and have memorized since elementary school. It's just finally specifying it. So let n be some integer, some number, and let d be a positive integer. Okay? So what this is saying is there are two unique integers. That's a key thing. Maybe I should say unique in bold, or at least italic. There are two unique integers, q and r, with r being between 0 and d minus 1. That's important. I think you can understand what r stands for after I show you this. And saying that n equals qd plus r. Okay? So q is the quotient, and r is the remainder. So it's just saying when you divide something by d, divide a number by d, equals some number remainder r. Okay, and this is all it's saying. The reason that works is because if you multiply d by that q and then add r, you get back n. And it's only a proper remainder if it was between 0 and d minus 1. Otherwise, d could have gone in one more time. Yeah? That's the idea. So that is the division algorithm. Pretty obvious, I think. You have been using it all your life, so it's probably very obvious to you. But it's actually not the easiest thing to prove. I think we'll prove it later in the class, but not now. Okay, we need more stuff. So, yeah, this is q is the quotient, r is the remainder, and if you ever see this in your book or like in math texts, they like to say div and mod. So I've been saying mod a lot, now we can say div a lot too. Those produce the quotient and the remainder. So you can say like q in this equation, q is equal to n div d. Okay, that's the idea. It's doing the integer division part and dropping the remainder. Okay. That's what that is doing. And then r is n mod d, which is, of course, your percent sign in C++. It's the modulus operator that you know and love already. So let's give a quick little example. Okay, let's do, I don't know, 7 div, I don't know, 3. And the answer is, we'll just do integer division. It's 2, right? 3 goes in twice with a little bit left over, but not quite to get 7. Okay, so that is 7 div 3, and then 7 mod 3, which you should know by now is 1. Okay, and the reason that works is because 2, which is the quotient, equals the original number, the original number 7. I was looking at the wrong equation. N, 7, equals QD, so that's the quotient, 2, times the divisor d, which was 3, plus the remainder, which is 1. 6 plus 1, yeah, that's totally 7. Okay, so it's just putting into words, putting into operations, stuff you already know. That is the division algorithm. Okay? So now, things get fun, because we can do mod with things and think about mod in a weird way. Okay, you already actually know about it, but it's still weird. I promise you that when you're starting out. So we're going to try and make it a bit less weird. This is a topic called modular arithmetic. Okay, so it will become soon apparent that it will be useful to have numbers that wrap around. Once you get to the biggest number, you wrap back to the smallest number. Okay, and you already use this in clocks, right? Once it becomes 12, then it becomes 1 again. Yeah, it just wraps around. So a nice way to wrap around with math itself is always doing mod m and picking that m. Okay, after every calculation that you ever do, you get modular arithmetic when you always do mod m after you do everything else. Okay? And when you do mod m, look what happens. Because, like, I don't know, let's pretend that our mod is 5. 0 mod 5, well, that is just 0. 1 mod 5, well, that's 1. All the way to 4 mod 5, that's 4. But then once you get 5 mod 5 again, ooh, that's now 0. 6 mod 5, oh, that's now 1 again. You see that? That is it wrapping around, and that is a 0. So it goes between 0 and your modulus minus 1. Okay, that's key. So all you have to do, if you want to do modular arithmetic, like if you're doing addition mod m, you say, you do your x plus y, you do your addition, and then you just remember to do mod m right after. That's all. That's all it means. Multiplication mod m. You do your multiplication, then you remember to do mod m right after. Yeah? That's not too bad. So let's do some addition mod n. Let's pick m being 5. Let's do, like, I don't know, 5 plus, well, we can't do 5. Let's say we started in it as well. 4 plus 3 mod 5. What's that? Well, it's 7 mod 5, which is, wrapping around, divide into 5. Okay, we get to 5. Then 2 more gives us 7. Yeah? It's the one after that one as well. That's addition mod 5. How about multiplication? 4 times 3, mod 5. How do you do that? Just to give us some practice. 12 mod 5, which is, interestingly enough, that's 2 again, isn't it? I wonder if we can get another one. Let's do 4 times 4 then. Just to make it different. 4 times 4 mod 5, that's 16. Which is 1. Okay, so that is modular addition, modular multiplication, modular arithmetic. Not too bad, I hope. With all of that, let's do this a bit more formally now. You can make out your total multiplication tables and addition tables just like you did in elementary school, but now we work mod m, we say. Okay, more modular arithmetic. So let's say you want to use mod m addition and multiplication. When you're doing that, and you're only ever taking mod m after doing addition and multiplication, you can't do anything else, you say that you're working in ZM, we say. So that's the idea. ZM is every number between m minus 1, so you're working with those numbers only. And you're using modular addition and multiplication. Okay, so that's what it means. There's a fancier term if you ever take an abstract algebra class, but we don't need to go there. You'll read about it in your book. Okay, so yeah, you'll say you're working in ZM, or you're working mod something. You're working mod m. So, for example, on the right are these mod 5 addition and multiplication tables. So, just like we did 4 plus 3 mod 5, you can write out this entire table. Like, okay, 4 plus 3 mod 5 is 2. Yeah? Or 4 times 4 mod 5 is 1. You see that? Which is nice and fun to think about. It's also quite nice, this will come up later, that the only way to get 0 when the mod is a prime is to have multiplied by 0, which is fun to think about. I'll just draw that for your amusement. So yeah, that is modular arithmetic. It's really not that bad. You're just wrapping things around. You're always doing mod m after you pick your m. Yeah? And another way to say all this stuff is the word congruence. So suddenly we have two numbers that used to be different, but now they're the same. Okay? Maybe I should write that. So we say that x is congruent to y mod m when, if you take mod m by both of those, mod m of x, mod m of y, you get the same thing. Okay? And it's written like this with three little bars, so that's like congruence, equivalence. It's equivalent when you're working mod m, when you're working in ZM. Yeah? That is the idea. So let's find some equivalent numbers, mod m. So for example, 0 is equivalent to 5 mod m, mod 5, sorry. 5 is equivalent to 10 mod 5. 15 is equivalent to 55 mod 5. They're all 0. Yeah? And this all works similarly with other things, like 1 is equivalent to 6, and it's also equivalent to adding 5, 11, etc. This is mod 5. Okay, it's different for every mod, for every modulus, but it's all a similar concept, I hope. Okay, so that is modular arithmetic in a nutshell, and I'd like to show you that, or I'd like to show you one nice thing about it before we use it to do some extra nice stuff later. So you can do mod m on each number before you do the plus or the times, and you still get the same result. So, for example, let's say we're working mod 5 again, and we want to do, like, I don't know, 77 times 63 mod 5. And that's no fun because those are giant numbers. I'm going to show you that it's equivalent to have done the mod first. That's equivalent to 77 mod 5 times, to make them smaller, 63 mod 5, and then take that mod 5 after. Those are going to be equivalent. Let me show you. So, I guess Racket's the best way to go. Whee! Racket. Let's say times 77, was it 63? It's that big number. And if we do that in mod 5, modulo 5, we get 1. And that's actually the same as doing the modulo first, like modulo 77, 5. That was 2, okay? And then the 63 mod 5 was 3. Well, now let's just do 2 times 3 mod 5. So 6 mod 5. I think you see that that's also 1. Ooh, that's nice. That saves us some work. That saves us from having large numbers over here. I hope you see that that will be useful. So the idea is you're allowed to make those numbers nice and tiny before you perform any operations. So let's prove the case for addition, and that'll be that. Actually, let me check the time first. Yes, so I want to prove this addition case to you, but let's do that in the next lecture, okay? So that is enough for this first one. Let us take a little break, and then I will see you in the next lecture where we will start with proving the addition case for this.